Welcome back to the training series for the Rehabilitation Cost Estimation tool for mining and exploration in New South Wales. This is Module 9. In this module, we will dive into the Tailings Storage Facilities input sheet, which calculates costs for decommissioning and rehabilitation of tailings storage structures. This sheet includes a default table and a user build table. The default table is simple to use and requires only the selection of a risk level, entry of a footprint area, and possibly some adjustments for growth media and low permeability layer material. The risk level selection references default capping thicknesses, growth media thicknesses, and engineering costs from the assumptions capping sheet. Furthermore, guidance on what risk level is to be applied to your tailings dam is provided in the Assumptions Inclusions column in the Cost Schedule sheet. Should you require further clarification, it is recommended that you reach out to the regulator directly to discuss the expectation of what rate is to be applied to the specific tailings facilities on your mine. We will enter 5 tailings facilities to show the different risk levels. We will name each structure, enter a GIS reference, if available, and the footprint area. Our 5 tailings facilities are TSF1 with a difficult risk level and 10 hectares, TSF2 with a high risk level and 50 hectares, TSF3 with a medium risk level and 100 hectares, TSF4 with a low risk level and 200 hectares, and TSF5 which has a very low level and a footprint of 10 hectares. If there are no adjustments to growth media and low permeability layer materials, this is all that needs to be done. However, the tables for growth media and clay for a low permeability layer can be used if we want to override the default assumptions for sourcing materials from off-site. We will add 1 hectare and a high risk level to columns 6 to 10 to demonstrate how these work. For growth media, the first row shows the calculated volume of growth media for the default rate based on the footprint entered, which is 1,650 cubic meters in the example. The next row shows the calculated volume sourced from off-site for the default rate, 330 cubic meters in this example. In this row, we can override the default assumptions. And the last row shows the cost adjustment made to the cost allocation for growth media. Let's see how this works. The first 2 columns show the default assumptions being accepted by leaving user override volume blank or making the volume equal to the default volume from off-site. No adjustment is made to the growth media cost allocation. In the third column, we can enter 0, indicating that all growth media will be sourced from on-site. Consequently, there is a downward adjustment to the cost. In the next column, we can make the user override volume equal to the full amount of growth media required, indicating all growth media will be sourced from off-site. As a result, there is an upward adjustment to the cost. The 6th column shows a case where more growth media must come from off-site than the default, but not all of it. If the default assumptions are changed, we must add notes to explain why. We can also select whether the material will be growth media or virgin excavated natural material, VENM. For the low permeability cap, the default rate assumes all material is available on-site. If clay must be sourced from off-site, we must enter the quantity and an upward adjustment is made to the cost. The user build table for the tailings storage facilities gives us more flexibility on the inputs and allows site-specific area entries, site-specific capping and growth media thickness, and a wider range of fleet selections. If the user build table is not showing, go to the left and select the Show in the drop-down box. This table is more complex and requires us to enter all the appropriate quantities to allow a proper cost to be calculated. We must enter quantities, even if they are 0 with a justification, to the following tables: cover embankments and ramps with rock, construct working layer, capillary break and low permeability layers, place top rock cover, source and apply additional capping, which is often not applicable, construct drains and water management, source and apply growth media and ameliorants, revegetate, permeability testing and engineering, maintenance and repairs of rehabilitated areas, and contaminated soil treatment. The first selection is similar to the default table with name entry, any notes we wish to add, risk level selection, and GIS reference. The risk level selection populates the default capping thickness and other items, but we can override these defaults further down the table. We will do an example of a high-risk tailings facility. The first difference to the default table is the requirement to enter several area quantities. We must enter a footprint area, which we will add as 100 hectares. For the embankment area, we will enter 20 hectares, and the ramps area will be 10 hectares. We now proceed down the sections and override default selections as appropriate. Remember, we must add justification when we override the default. We will leave the cover embankment and ramp section as suggested by the tool, changing only the dozer selection from D6 in all cases to a D8. In this example, we will assume 20 hectares of the cap has already been completed, so for construct working layer, we will override the 100 hectare footprint with 80 hectares. We add a note to inform the regulator and change the dozer from D6 to D8 in all cases. We do the same for the capillary break area, overriding the 100 hectares with 80 hectares and providing a justification. In this example, we have undertaken studies to show the capillary break layer only has to be 0.3 meters thick rather than the default 0.6 meters, so we enter 0.3 to the thickness override and provide a justification. We can see the tool is using the 80 hectares area override and the 0.3 thickness override to calculate the volume required for the capillary break layer materials. We will leave the other selections the same, except for the fleet and distance for load and haul of capillary break materials, which we will change to the medium fleet and 2,500 to 3,000 meters options. Again, as 20 hectares of the cap has already been complete, we enter 80 hectares for the low permeability layer area, as for the working and capillary break layers. We will leave the thickness as the default. In this example, there is no clay on-site, so it must all come from off-site. However, we have negotiated a rate with a supplier of clay and will enter that as an alternate rate. When we select offsite from the source dropdown, we can see all the costs associated with the borrow pit are set to 0. We move to the offsite section and override the default per cubic meter rate with our negotiated rate, which is $35 per cubic meter delivered to site. We override the transport cost by entering 0 to the load and haul alternate rate. We will leave the rest of this section as suggested by the tool. For the top rock cover, the area is the footprint area of 100 hectares minus the embankments, which we entered at the start as 20 hectares. We will accept the defaults except for the fleet selections, which we changed to 2,500 to 3,000 meters one-way distance and the dozer to a D8. Additional capping is not often required and is set to 0 by default. However, we will enter quantities here to demonstrate the calculations. We match the suggested area in each case, but do not require any additional rock, so we leave that blank. The default assumption for drainage is 10% of the footprint area. In our example, we can demonstrate the area does not receive rain often and drainage can be minimal, so we override the 10% with 5%. We will leave the drains at 4 meters width. For growth media, the tool calculates the sum of the footprint area plus embankment area. In our example, 20 hectares of the cap is complete, so we will enter 100 hectares, which is 100 hectares for the footprint minus 20 hectares that has already been capped, plus 20 hectares for the embankment. For our example, all growth media is on-site, and we have an engineering study that accurately calculates the volume of growth media required. Our study says we need 120,000 cubic meters. We cannot just override the number calculated by the tool to the volume from local on-site supply row, as the tool will assume the deficit has to come from off-site. Instead, we change the thickness to 0.12 meters in this case, so the tool calculates 120,000 cubic meters. Then we make the volume from local on-site supply row equal to this number. The tool now sets the off-site cost to 0. In our example, studies have shown we need to amend the growth media with gypsum and biosolids to create a soil structure conducive for vegetation growth. We will add 100 hectares here to match the growth media area and select gypsum and biosolids. We do not have any quoted rates for supply of gypsum and biosolids, so we accept the defaults. We will enter the same area to the revegetation table and select native seed and matching selections throughout this section. We will leave the permeability testing as suggested by the tool, but we will reduce the engineering cost to $2,500 per hectare because many of the studies have been done. Remember to leave notes when we enter alternate rates. To demonstrate how several land treatments may be applied, we will assume all these are required and enter 10 hectares along the columns. That is, 10 hectares for pest management, land management of undisturbed areas, existing rehabilitation repair minor, moderate, major, and total failure of landform, and maintenance of areas that are shaped and seeded and revegetation has been successful. We have no contaminated soil, but are required to produce an extra report to confirm that the capping of the 20 hectares was successful, and we have a quote for this report. It is $50,000, so we add this to the additional rows section. As for all the sheets, the subtotals for each table are shown in the black lines at the end of each section, and then the total for each column is shown at the top of the sheet. For this tailings sheet, the tool also shows the per hectare rate for the default and the user build tables. The total for the sheet is shown on the left-hand side, and then above that is the total for the entire RCE, so we can see in real time how quantities entered to the local sheet affect the total RCE. Let's jump over to the RCE summary to see how the total is building up. We now have rolled up costs for infrastructure area, infrastructure mine entries, beneficiation facilities, and tailing storage facilities.